Professor Ullman is the co-recipient with John Hopcroft of the 2010 IEEE John Foyle Neumann Medal for laying the foundations for the fields of automata and language theory, and many seminal contributions to theoretical computer science. So please, Professor Ullman.
Thank you very much. Let's see. Okay, so I want to talk to you about something completely different. What I'm concerned about is the design and analysis theory for parallel computation. As many of you may know, Moore's law sort of died, at least as far as single processors are concerned, actually many years ago. And the way we make things run faster and faster these days is by using parallel computation. But writing parallel programs is hard, and as a result, a number of programming systems have been developed recently, and they make parallel programming easy. Okay, you don't actually have to think parallel, you think serial, and the system makes it parallel for you. I'm going to talk in particular about the first of these systems called Mapreduce, or it's Hadoop is the publicly available implementation. And I want to talk about how you design algorithms using a Mapreduce system. And this requires knowing, well, not only having good design sense, but knowing what the limitations are. You don't know that you have a good algorithm unless you can prove that there are no better algorithms to do the same thing. So I want to talk about, focus on a particular example of a design problem from Mapreduce, and then talk a little bit in general about how you think about these problems. Okay, so first of all, as I said, okay, Mapreduce systems give you two big benefits. Okay, they let you get parallel programs written without actually having to think parallel. You write serial code. I'm going to say it's in Java. That's a common language. There are versions of Mapreduce and other systems that use other languages as well. So you don't have to write parallel code. And the other is, when you have 1,000 processors working for you, something can easily go wrong before the job finishes. You don't want to have to yourself figure out what to do when something goes wrong. And so the system, like a system like Mapreduce, will do that for you. Okay, well, as I said, you don't really get anything for free. You're limited in the case of Mapreduce, at least in a somewhat subtle way, as to what your algorithm can actually look like. So what I want to really talk about is, what are the limitations? What does programming in this Mapreduce paradigm tell you about, how does it limit your the kinds of algorithms that you can write? Now, I don't know how many of you have actually seen Mapreduce before. I want to go through the idea in some detail. Okay, first of all, a Mapreduce job takes a file, possibly a large file, it could be a terabyte-sized file. But the file consists of some number of input elements. There's a type, one type for the element. So it could be a file of integers, it could be a file of documents, just anything really that, let's say, that is describable as a Java type. Now, you write a serial program called the map function, let's say, again, in Java. And the Mapreduce system, say Hadoop, is going to apply the map function to every input. And in principle, it can do this in parallel. That is, you have as many machines running in parallel as there are inputs. Probably you're going to have many fewer machines. But I want to talk about a mapper is the application of the map function to a single input. And again, normally you don't have complete n-way parallelism. You group some often fairly large number of mappers into a single unit of parallelism called a map task. Okay, so the map tasks will operate in parallel, but within a map task, the mappers are applied serially. Okay, now the map function is of a very limited form. It has to produce a set of key value pairs. Okay, and you can choose whatever type you want for the keys. You can choose whatever type you want for the values, but you get to choose one key type, one value type. And again, the map function will apply. Think of it as in parallel. It's applying to each input, generating from each input key value pairs. But again, the map function operates on a single input. There's no way to, at this stage of the Mapreduce process, to get connections between two inputs. Okay, it's all independent. Okay, now imagine all the mappers run. You map all of the inputs. The system collects all of the key value pairs that are generated by all the mappers and groups them by key. Okay, and what it actually then is it forms for each key a single object consisting of the key value and the list of all the associated values that all the mappers have generated with that key. Okay. Now, you as the programmer, you've also written another function called the reduce function, and the reduce function takes one of these key list of values pairs and does something, creates some output. Okay, so I want to talk about a reducer then is the application of the reduce function to a single key and its list of values. And again, there's a unit of parallelism would be the reduce task, which would be typically a collection of many reducers. Okay. Again, as I said, each reducer will produce some output. The output of the job then is the union of what each of the reducers produce. So here's the picture I'd like you to bear in mind. Again, you have an input file. Each element of the input file is passed to its own mapper. In this picture, I've shown you that each mapper is producing some output for each reducer. Typically, a mapper will produce output for only one or a small number of reducers, but it could, in principle, produce something for each of the reducers. And then the reducers, again, operate in parallel, and the output is the collection of what all the reducers produce. Okay. Now, each MapReduce algorithm then has a cost. One thing which you might worry about is the execution time of the mappers and reducers. And again, remember, things are going on in parallel, so the total amount of computational work and the wall clock time, that is how long it finishes, you don't quite know how those relate. The wall clock time will be smaller if you have lots of parallelism, that is, lots of processors running at the same time. But you can't get away from the fact that you have to execute each mapper, you have to execute each reducer, and the total amount of time that these spend is the execution time. Then there's the communication cost. That is, each mapper, really map task, runs at a particular compute node, and it's going to feed its output, those key value pairs, to different reducers, which will then also run, each reducer again will run at some compute node. We assume that there's lots of parallelism, so there are lots of compute nodes. Typically, you're going to have to take each key value pair generated at some compute node, move it to some other compute node. If you're really lucky, it'll go to the same compute node, so you don't actually have to communicate it. The chances of that are, it's only 1 over the number of processors or compute nodes you have working. So I'm going to assume it's 0. The probability of being lucky is 0, and just count the communication cost as the number of key-valued pairs that you have to transmit. Okay. And I might say not always, but very frequently, it's the communication cost that limits how fast you can, the total amount of time that the Mapreduce job takes. Okay, so now with that having been said, I want to talk about a particular problem. It was finding interactions between two drugs, and in particular, whether two drugs taken together will cause, or have some non-zero probability of causing a heart attack because you took both drugs at the same time. Turns out there are about 80 such pairs of drugs that are known. Anyway, I want to just show you, if you do the naive thing, even though the amount of data involved was really not very big, if you do the wrong thing, your job just will not run. Okay, and then I want to talk about how you, in fact, make it run by lowering the communication while keeping the computation costs the same. So this is actually a story from we teach this data mining project course where teams of students propose their own problem to work on. They sometimes bring their own data, sometimes they use data that we provide. But this was a team of students. It turned out, by the way, that while I'm going to essentially criticize their first attempt, they actually, at the end, wound up doing some really good work. They were able to identify 40 of the 80 known pairs, and they found 2 pairs that were not actually yet known, pairs of drugs that cause heart attack. So they had data from the Stanford from the Stanford Hospital. They had data for 3,000 of the roughly 6,000 drugs that are in common use. The reason they didn't have the other 3,000 was because they're so rare that there just wasn't enough data to have a statistically significant statement about them. But for each of these drugs, they knew which patients over 20 years had been administered the drug and what happened. In particular, did they have a heart attack shortly after receiving the drug? And just to give you a scale of the data, it's about, on average, a megabyte per drug. That's on the average. Obviously, some drugs like aspirin, I'm sure, lots more than 1 megabyte, some less. So that's 3 gigabytes of data. That's not much, right? It fits on your laptop. Okay, so you'd think it should be an easy problem. Well, it wasn't. Okay. And again, as I said, their goal was to determine pairs of drugs that, when you take together, will increase the risk of a heart attack. So in statistical terms, they're going to do a chi-square test on each of the 3,000 choose 2, or about 4.5 million pairs of drugs. Okay. So they wrote their first Mapreduce algorithm, and it did the following. First of all, the key type will be pairs of 2 drugs. And the value type will be the records for these drugs. Again, so each value on the average is a megabyte long. Okay, so what does the mapper do? For the mapper for drug I will generate for all other drugs J besides I a key value pair that has as the key the set containing I and this other drug J, and as value the record RI, the record of what happened with drug I. Now, from the point of view of the reducer for the key ij actually gets two key value pairs. The key, of course, will be I and j. There'll be two values, one the record for I, the other the record for j. And the system behind the scenes, again, remember, is sorting all those key value pairs according to the key and then lining up the record, the two records as a list. So here's a simple example of what's happening. Now, in this case, I'm just going to talk about 3 drugs rather than 3,000 drugs. But the mapper for drug 1 will generate the key value pair. The key will be 1, 2. 2 is one of the other drugs besides drug 1. And we'll attach to that the value, which is the drug 1 data. And then it'll take another drug is drug 3, so it'll generate the key 1, 3. And attached to that the drug 1 data. And then the mappers for drugs 2 and 3 do the analogous thing. And then, behind the scenes, the system sorts by key and then reformulates it as a key and a list of values. So, for example, the reducer for 1, 2 gets the key 1, 2, and the value list is the drug 1 data and the drug 2 data. Well, does anybody see why this thing didn't work? Okay. Well, let's see. You had 3,000 drugs. How many key value pairs did you generate for each drug? 2,999, because that's the number of other drugs besides the one for the mapper. And then the key value pair is on average a megabyte long. Okay. Well, you put that together, you get 9 terabytes. And they were running on the Amazon AWS system. So you got to communicate 9 terabytes over 1 gigabit Ethernet lines. Now, you multiply that out, it's about 90,000 seconds, or a little over a day. Okay. Well, it's a little more complicated than just the 90,000 seconds, because you've actually got not just 1 gigabit Ethernet, but many of them connecting various compute nodes. On the other hand, you also have other jobs being run by AWS at the same time, and they're competing for those same Ethernets. So it's a little confusing, but bottom line is after 8 hours, they killed the job, had not finished. And so I got an email from them saying, hey, we're running into a little problem. Okay. And so we met in my office and took a look at what the problem was, and we came up with a better algorithm. Okay. And I'm just using some round numbers. This wasn't exactly what they did. But we said, let's group the drugs into groups. So let's have 30 groups of 100 drugs each. Okay. Now, in the new algorithm, keys are pairs of group numbers, not pairs of drug numbers. And the mapper for a drug, say I, will produce 29 key value pairs. The key in each case will be the set containing I's group and one of the 29 other groups. Okay. And the value, it will still be the drug I's record. In this case, you have to actually tag it by I so we know which drug's record that is. Okay. And now, let's look at it from the point of view of the reducer. Okay. You get the reducer for the pair of groups M and N will get, of course, the key set containing Mn, and a list of 200 drug records, the drugs belonging to these two groups, M and N. And it has to compute, it has to run the chi-square test on each pair of drugs, one from group M, one from group N. Well, there's a small matter that you also have to compare drugs that happen to belong to the same group. You don't want it, you could do this in any of 29 different reducers. You have to have some rule for deciding who's going to do it so you don't redo work. And if you do it right, then each pair of records will have each pair of drugs or records will have the chi-square test run at exactly one reducer, so the computation is exactly the same. But the good news is that the communication is much less. You still have the 3,000 drugs. The records are still a megabyte long, but now the replication is only 29 rather than 2999. Okay, that gives you communication cost of about 87 gigabytes, or about 1/100th of what it was before. And in fact, they finished in about an hour. Okay, so they got the thing done. Okay, so with that, I want to talk a little bit about this again. A new theory of design and analysis of Mapreduce algorithms, and well, here are some of the terms that I will introduce one at a time. The first thing we want really is a model for I'm going to say it's a Mapreduce algorithm. What it really is it's a model for the problem itself. Okay. Well, you have a set of inputs. In the example that I just gave you, the inputs of the drug records. There's a set of outputs. In the drug interaction problem, the outputs are pairs of drugs. Either you say a bit, either it could be just the chi-squared value itself, or a bit saying, yes, this chi-squared value is too high. There is an interaction, or no, it's not too high. But then you have a many-to-many relationship between the outputs and the inputs that are needed to compute that output. So, for example, for each pair of drugs I and J, the output for IJ requires the input I, the input J, and no other inputs. So, for example, here is the many-to-many mapping for 4 drugs. Notice, for example, that the output 1, 2 depends upon the drugs 1 and 2 inputs, but not the other 2 drugs, and so on. Here's, this is sort of the input-output matrix from input-output mapping for matrix multiplication, except it's really just a little piece of it. That is, the output in position row I and column J depends on the entire row I of the first matrix and the entire column J of the second matrix, but nothing else. Okay. So the whole input-output mapping is this overlaid for all values of I and J. Now, again, one of the key elements of this design theory is reducer size. I'm always going to call it Q, and it's defined to be the maximum number of inputs that a reducer is allowed to have. That is, again, it's the length of the value list associated with a key. Okay. Now, why do you need a limit? Well, in order for things to run reasonably fast, you really need to be able to operate a reducer in main memory. If you have to start shuffling things from disk, you're going to run 1,000 times slower, roughly. You might even want to make Q even lower, because the lower you make Q, that is, the smaller you make the reducers, the more parallelism you can get. Okay. But so at any rate, the only message I want to give you is a low value of Q is good. High value may be bad. The other element of the story is the replication rate, which I'll denote by R, and that is the average, I'll say this, the average number of key value pairs that are created by a mapper. Okay. And you can think of that as the communication cost per input. Well, the communication cost is actually going to be that value R times the cost of computing of communicating one key value pair times the number of inputs. But the R is sort of the thing that you can control. Everything else, you know how many inputs you have. That's just the data file you have to work on. You know how big they are. So again, let's talk about sort of generalize the algorithm. I gave you really two versions of the same algorithm for drug interaction. So let's generalize it. You can have G groups, and we can assume that there are D drugs. In both versions that I gave you before, D was 3,000. In the first version, there were 3,000 groups with one drug per group. In the second, there were 30 groups with 100 drugs per group. But you can now, just the obvious generalization, any number of drugs, any number of groups. Now, what's the reducer size? Well, again, if you think about how the algorithm works, it has to take two groups. The reducer has to get the inputs from two groups. So therefore, well, there are D over G drugs per group, and therefore Q is 2 times D over G. Okay. Now, what's the replication rate? Well, you have an input is sent to G minus 1 reducers. That is, the reducer corresponding to the group of that input and any of the G minus 1 other groups. I want to assume that all my parameters are large. Like, so G minus 1, I'm just going to call it G. And so I'm going to just say that the replication rate is essentially the number of groups. So therefore, you have this equation, Q is 2D over G. I could say G is R, so I can say Q is 2D over R. I like to switch R and Q because Q is something you can control. R is what you get. Okay, so the formula is that R is 2D over Q. And so what that says, you see, this is the trade-off. It says the smaller I make Q, the larger the replication rate is I'm forced to accept. Okay? If I want a small replication rate, I have to make a really big Q. But that might cause me to have to go to disk when I run the reducers and so on. So, there's this trade-off that you have to deal with. Okay. At any rate, I gave you a family of algorithms. That gives you an upper bound on R. It says I could certainly use one member of this family of algorithms. Given any Q, I could use one algorithm with really Q equal to the number of Q essentially determines the number of groups for the version of the algorithm I want. So I know I can get an R that's no bigger than 2D over Q. And now the question is this the best we can do? And right, if you want to have a design theory for algorithms, you need to know how good can I make it? Do I have an algorithm that's as good as any algorithm to solve the problem? So if the input-output mapping is is sort of an abstraction of the problem, what we call a mapping schema is an abstraction of a solution or an algorithm. Okay. So the mapping schema, for a problem, again, a problem is an input-output mapping. And Q, given also the mapping schema takes Q as a parameter, that is Q is the reducer size. So the mapping schema then will assign inputs to each input to one or more reducers, and it has to satisfy two conditions. One, you can't assign a reducer more than Q inputs. Well, that's the definition of Q. It says that's how many inputs you're allowed to send to one reducer. But the second condition is more important. It says that this actually has to be an algorithm that solves the problem. And I claim that in order to solve the problem, for every output, there has to be some reducer that gets all of the inputs that output needs. Okay, if there is, that is, we're going to say that the reducer will cover that output. If an output isn't covered by any reducer, then there's no reducer that gets all the inputs needed to compute that output. The algorithm cannot work, cannot really solve that problem. Okay. Conversely, if there is a reducer that gets all the outputs that's needed, you can, again, this is an arbitrary, reducer is an arbitrary Java program. You must be able to write the code that will actually compute the output correctly. So that's so it should be good enough that the output is covered to say that you can in fact solve that this mapping schema can solve the problem. Okay. Well, again, my feeling is that a Mapreduce Mapreduce algorithms correspond to mapping schemas. And the fact that there has to be a mapping schema to solve the problem is why writing Mapreduce algorithms is not just the same as writing parallel algorithms in general. Okay. So let's just take a look at the limitation that the consequence for the drug interaction problem. Again, the problem will be, again, we want to compare all pairs of D drugs using a reducer size Q. Well, each drug has to meet each of the other drugs at some reducer. And there has to be some reducer that covers each pair. Well, suppose I send a drug to some reducer X. Okay. Well, again, since the reducer gets at most Q drugs, it can only, this drug X can only meet Q minus 1 other drugs there, so that reducer can only cover X, Q minus 1 pairs that contain X. It might also cover some other pairs. Okay, so a consequence, therefore, is that each drug has to be sent to at least, well, it's a formula. Again, it's got to meet D minus 1 other drugs. It can only meet Q minus 1 drugs at one reducer. So the number of reducers that get that drug has to be at least the ceiling of D minus 1 over Q minus 1. And again, I want to assume that D and Q and R and everything are large. So what you really get is that R is at least D over Q. That's interesting, right? Because remember, we also have this family of algorithms that say that R is at most 2D over Q. So we got this factor of 2. Okay. Well, I won't leave you in suspense. But it turns out that the family of algorithms I've described are not the best. There's a much more complicated family of algorithms that will give you more or less R, approximately R is D over Q. So the lower bound is really tight. The upper bound that I gave you is not quite tight. Okay. Well, okay, just to sum up, finish the story. I gave you one example of this all pairs or drug interaction problem. There are a couple of other things that have been analyzed by me and some colleagues. A matrix multiplication is an interesting example. There is a trade-off very similar to the drug interaction problem, but there the obvious algorithm is in fact tight, as the upper and lower bounds on replication rate are the same. But the interesting thing is, remember, this theory only applies to one round of Mapreduce. You can have a round of Mapreduce, then you can have another round after that using the output from the first round and any sequence of Mapreduce rounds. What we can show is that there's a two-round algorithm that substantially beats any one-round algorithm, okay. Which was a bit of a surprise. Let's see, we did a long time ago, we did something on probably Hamming distance 1. That is, the inputs are bit strings, and you want to find those pairs of inputs that differ in exactly one bit. And then you have a trade-off. It's rather different from the trade-off in for the all pairs or the matrix multiplication. One of the interesting things is, even though we did this a good number of years ago, nobody's ever been able to do the trade-off for Hamming distance 2. That is, inputs, again, are bit strings. Find the pairs of bit strings that differ in 2 bits. Let's see. More recently, we did marginals of a data cube, and again, we get a tight bound there. Marginals. If you think of your data, if your data is n-dimensional, then the marginals, or kth order marginals, are obtained by you fix k of the dimensions, pick k particular dimensions, fix them in all possible ways, and then sum over all the other n minus k dimensions, and that gives you a marginal. Okay, so you want to compute all the marginals of kth order. Again, we have exact bounds on the limitation for how you do this using Mapreduce. Okay, so with that, I will put it to bed. I guess. There you go. Okay. Thank you.
Thank you very much, Professor Ullman, for your lecture analyzing the Mapreduce with the drug interaction, with an example of drug interactions. Thank you very much.